Okay, so good morning everyone. We meet the second day of this complex variables course. So the first ritual that we have to do every day is this putting up of this notice on course content and the relevant information. So let's get that down in the slides, right? All right. So having done that, let's proceed on to the next chapter. Today we start a new chapter, chapter 2, differentiability of functions of a complex variable, right? And under these there are three parts: Cauchy-Riemann equation, conformal mappings and harmonic functions. Conformal mappings, I am just going to tell you what it is, we are not going to do much with it. It will mostly appear in exercises. Conformality will appear in a couple of exercises, and at that time I will explain to you what these are. And harmonic functions. You are already familiar with harmonic functions, the PDE part, but we'll just touch upon it briefly in this part also. All right. Okay. Now we need a few basics from your calculus courses. So we need to recall a few basic facts. So first we'll begin with your recapitulation. So first we recall a few basic facts from calculus. So suppose you have a subset of the complex plane. We say that omega is open if for each a in omega, so take a point a in omega, then you should be able to find r positive such that if you draw a disk of radius r centered at a, that disk should lie completely in omega. Is that clear? So, and this should happen for each and every point. Given an arbitrary point a in your set omega, given an arbitrary point a in omega, you should be able to find an r. Of course, r will vary, r will depend upon the point a. If you take a point over here, the r will be small. If you take a point here, the r will be large. R will depend upon a, never mind, but there should be one such r. It could be very small, but whatever it is, there should exist an r positive such that the disk of radius r centered at a should be completely contained in your omega, right? Omega could be could have an arbitrary shape, like it could be like an omega, like an amoeba, right? And it does not have to be, it may even have some holes inside, like an amoeba has food vacuoles, no? So it could even be a, for example, you can think of the region between two concentric circles, right? That's also an open set, right? This is clear, the concept of an open set, and we'll be working with such open sets. Our functions will have domains which are open sets, correct, unless otherwise specified. Now another thing that we discussed in the differential equations course, but I will recapitulate here. Okay, before that, an open subset of C is said to be connected if any two points A and B can be joined by a arc lying entirely in omega. This is not really the definition of connectedness, this is a definition of path connectedness, but for an open set, it is a fact that connectedness and path connectedness are one and the same concepts. The concept of connectedness is somewhat different in topology. However, for open subsets of the plane, that is all that we are concerned here, for open subsets of the plane, there is no distinction between connectedness and path connectedness. So, we may as well take as our definition, we may as well take it as a definition that connected means path, means that any two points can be joined by an arc, alright. So, is it clear? So, the picture shows a connected set here, and this region consisting of these two pieces is a disconnected set. I can take a point here and I can take a point here, the arc joining them will spill out of the domain, correct, alright. So, is the concept of connected set very clear? So, now we are going to always refer to an open connected set as a domain. An open connected set is called a domain. So, when I say domain, it means it is open and it is connected. Now, what is the definition of a convex set? We already discussed this in our differential equations 1 course. Many of the differential equation 1 participants are also here, and they will and you should recall it, that a set is said to be convex if given any 2 points A and B in that set, the line segment joining A and B should lie wholly in the set. So, the interior of a disk is a convex set, right. There is an exercise which asks you to show that the interior of an ellipse is a convex set. You have to do it analytically. You will have to prove it. It's not just enough to draw a picture and pick up 2 points and show that it's not just enough to demonstrate the thing by a picture. You have to actually prove it, right. So, the exercise says show that the interior of an ellipse is a convex set. You have to do it analytically. We already discussed this example in the differential equations course, but never mind, many of you have not been in the differential equations course. So, it is worthwhile putting this exercise again over here, right. So, that what is the set Ta plus 1 minus Tb, excuse me, there is a mistake here, Ta plus 1 minus Tb, right. You have taken 2 points A and B in omega. The line segment joining the 2 points is Ta plus 1 minus Tb, right, alright. So, that made the correction now. So, the line segment joining them should lie entirely in omega. Is the definition clear of a connected of a convex set? So, now we have the notion of an open set, we have the notion of a open connected set, and we have the notion of a convex set. Is a convex set connected? Yes, because the arc is really the line segment itself, correct. Now, the next concept that we are going to discuss is that of a star shaped domain. What is a star shaped domain? Again, we have discussed this in the differential equations course. So, let us recapitulate it here. What is a star shaped domain? When is a domain said to be star shaped? Yes, if there exists a point A in the domain such that any point in the domain can be joined to this distinguished point, correct. Again, a domain is said to be star shaped if there exists a point A such that every point in the domain can be joined to this point by a line segment lying wholly in the domain, correct. What is the difference between a convex set and the star shaped domain? There is a slight difference. Is a convex set star shaped? Yes, any point in the convex set can be taken, because and to take any other point and the line segment joining lies wholly in it. But the point is that a domain may be star shaped with respect to a distinguished point, correct. So, unlike a convex set where I can take any 2 arbitrary points and join the line segment, here one of the points is fixed. Here one of the points is fixed. I can't take any 2 points. In the convex set I could take any 2 points and I can join them by a line segment. Whereas for a star shaped domain, there exists one fixed point and the second point is variable. The second point can be arbitrary and the second point is joined to the fixed point, the chosen point, the distinguished point. Is this correct? So, a convex domain is star shaped but not conversely. Can you give an example of a domain which is star shaped which is not convex? Take for example the red cross, medicine, the center, it's star shaped with respect to the center, but if I take two points in different arms of the cross, the segment will jet out, right, it will spill out of the domain. So, here is the next slide formalizes all these things. So let us read this carefully. A domain omega is said to be star shaped if there exists a point A in omega such that given any z in omega, the line segment joining z and A lies entirely in omega. Right? This is analytically described over here. What I had described in words has now spelt out analytically. The set Ta plus 1 minus Tz 0 less than or equal to T less than or equal to 1 is contained in omega. Correct? Trivially, a convex set is star shaped. The converse is not true. Here you see a picture of a domain which is star shaped but not convex, because if I take these 2 points, then the line segment joining them spills out to the domain, whereas it is star shaped with respect to this point over here. I can reach any point in the domain from here, but not from here. Correct? Is it clear? Star shaped domain. The next exercise asks you to show that the set of complex numbers C minus xy such that y equal to 0, x less than or equal to 0 is star shaped at 1, 0. That is, you have taken the plane, you have taken the complex plane and you are cutting out the negative real axis, and that is star shaped with respect to 1, 0. That is an exercise. It is an easy exercise. This is also an exercise that I gave with the MA 108 course, right, in the differential equations course. This exercise also appeared there. Now, the next thing that I would like you to recall is the definition of continuity. Yes, is there a method for finding the point? There is no fixed method. I mean, it will depend upon the domain. I mean, there is no easy way of determining. In fact, the domain can be given analytically, and domains can be quite complicated, and whether it is star shaped is not, it's something that has to be verified in each and every situation by drawing pictures and whatnot. No, it will be star shaped with respect to some specific point, right? So you have to determine that point with respect to which it is star shaped. The domain will, to say whether the domain is star shaped means that you have to find that specific point, you have to find that distinguished point with respect to which it is star shaped. Usually when you draw pictures, it will become very clear what is that point. The domains that we shall be interested in are nice domains, geometrically described, like an interior of an ellipse or the plane minus the negative real axis, whatever. It will be quite clear to you what that distinguished point is. A verification can always be done. Geometrically it will become very clear, and analytically you have to verify it. Now, what is the definition of a continuous function? Suppose you have a domain omega and you are given a function f from omega to c, a given function. When do you say that this function is continuous? Usual epsilon delta definition. Given any epsilon greater than 0, there is a delta greater than 0 such that mod z minus a less than delta implies mod fz minus fa less than epsilon. Now remember that we are looking at a open set, and A is a point in the open set, and so, and the definition asserts there exists a delta, right. So there exists one particular delta, any smaller delta will also work. The moment the thing holds for one particular delta, it will continue to work for a smaller delta also, and then I can choose the delta small enough so that the disk is completely contained in omega, right, because it is an open set. So I do not have to put in any qualifications here that z belongs to omega and z minus a less than delta. That qualification is not required here, because the delta can be chosen to be small enough at the outset so that the disk of radius delta centered at A will be contained in omega. Alright. The usual standard definition of continuity of functions of a real variable, the same thing simply carries over for the functions of a complex variable. There is no change at all as far as continuity is concerned. there is, it's a matter of convention. What is the difference between a domain and a region is a matter of convention. Some people use the word region, some people use the word domain, and it depends, the convention varies from book to book. So it's better to put the conventions on paper. For us it's a domain. I call a domain as an open connected set as a domain. Some people call an open connected set as a region. Some people would say a region is open but a domain is connected, etc. There are all sorts of variants. The point is, the reason why people prefer the word region rather than domain is that in mathematics, we are talking about functions, and functions come with a certain domain, right? I mean, when I am talking about a function in general, it has a domain and a codomain. There the word domain has a different meaning, whereas all the functions that we are going to be considering will be functions defined on a certain domain as it is described here. We are looking at nice functions, e to the power z, sin z, cos z, a power series, and so on. So we are not going to be looking at general functions as in algebra or topology or whatever it is. So for us this is good enough. So we will use the word domain, I mean, to mean in the restricted sense that it is a open connected subset of the complex plane. Sometimes I may need a function which is defined on a interval. What is a path or an arc? An arc is a continuous function from an interval to C. So for this particular function, the domain is an interval. The context makes it very clear. No? If I am talking about an arc or a path, the domain of the path is an interval. Here the word domain means, I mean it in the set theoretic sense. The context makes it very clear. There is no need to distinguish. You could use the word region also if you like. I mean, we can use the two words interchangeably if you will. There is no harm, because the connectedness will appear only in very specific contexts. For most theorems, connectedness will not play any role. Connectedness will play a role later, much later, and if at all it does any role, if at all it plays any role, so not a problem. Any other questions? So it's not everything is clear. What is the domain? What is an open set? What is connected, star shaped, convex, and the definition of continuity. Same definition as the real variables. Now, what is the definition of differentiability? When is a function said to be differentiable? First of all, what is it that you have studied so far? You have studied functions on the real line. So let us take a function from the real line to the real line, but your function may not be defined on the whole real line, right? It may only be defined on a certain subset of the real line. Tan x is not defined at minus pi by 2 and pi by 2, correct? So what is the definition of a derivative, a function of a real variable? You need a function defined on a open interval, isn't it? The definition of derivative, you stipulate that the function is defined on an open interval. So take an open interval I and you take a function f from I to R, right? Take a point A in the interval, and what is the derivative? Derivative is the limit as h tends to 0, f of a plus h minus f of a upon h. If the limit exists, then you say that the function is differentiable at a, and the value of the limit is called the derivative, right? Now we are going to be looking at functions of a complex variable. Instead of an open interval, we are going to be working over a open set, omega. Everything else is going to remain the same. Definition. So let omega be an open subset of C, and f from omega to C, a function, a given function. We say f is complex differentiable at a belonging to omega if the limit f of a plus h minus f of a upon h, limit as h tends to 0 exists. The value of the limit is denoted by f prime a, and I am going to call it the derivative of f at a. That not really written down in the slide, but I am telling you. I am going to call f prime a the derivative. What is the meaning of this statement that limit as h tends to 0 f of a plus h minus f of a upon h exists? What is the definition of a limit? Very similar to the definition of continuity. Given a function f from a complex from a open set in C to C, when would you say that the limit of f of z as z tends to z naught exists and is L? What is the meaning of this statement? It means given any epsilon greater than 0, there is a delta greater than 0 such that 0 less than z minus z naught less than delta implies mod fz minus L less than epsilon. This is the usual epsilon delta definition of limit. Same thing carries over. Whatever you have studied in the real analysis simply carries over word for word, correct? And this is the definition of a derivative. And if a function is, if this limit exists, you say that f is complex differentiable at a. F is complex differentiable at a, and the limit is called the derivative of f at a. Is that correct? All right. So now the next thing is that if the function is differentiable in this sense at each and every point of the domain, you will say that the function is complex differentiable over the domain omega. All right. Let us just put that down. So if f prime of a exists at every point of the domain, then the function f is said to be complex differentiable throughout omega, and now we have a new function, right? Z going to f prime z is called the derivative of f, or the derived function. That is a new function f prime. From you have f, and then I can calculate f prime, and I have a new function f prime, the derivative of f, correct. Next is that the rules of calculus, rules for calculating the derivative. The remark says that the usual rules of calculus apply and the proofs go through without any change. And we just list the rules of calculus in the next slide. What are the rules of calculus for with regard to derivatives? Derivative of sum is the sum of the derivatives. Derivative of product, you have the product rule. Derivative of quotient, you have the quotient rule, and you have the chain rule, right? The product rule, the quotient rule, and the chain rule. There is no difference. They simply go through word for word. All right. So now you have f from omega to C. Omega is an open set, and the thing is complex differentiable at a point A in omega. Then first of all, the function is continuous at the point. Differentiability implies continuity. Proof is the same as in the real variable case. Then you pick two functions f and g from omega to C. Omega is open as usual. They are both complex differentiable at A. Then the sum of the two functions is complex differentiable at A. The product is complex differentiable at A. The quotient is complex differentiable at A, provided g of A is not 0. Correct. Moreover, the derivative of a sum is the sum of the derivative. To calculate the derivative of the product, you have to use the product rule, and you have to calculate the derivative of the quotient, you have to use the quotient rule. Have I written down these rules correctly? Is there any mistakes? Should I make any corrections here? No corrections. The quotient rule is correct, right? All right. Clear? And the proofs, they are the same as in the real variable case, and it's a complete waste of time to prove them all over again. If you have forgotten the proofs, just read Thomas and Finney for the real case and just write down the same thing for the complex case, word for word. there is no change at all. Alright. Now we come to the non-trivial chain rule. What is the chain rule? How do you state the chain rule? You have two functions, f from omega to c, correct, and then g is from some other omega tilde to c, correct. You have two functions, so they will have their own domains, omega and omega tilde. But what is the important property of omega tilde? Omega tilde should contain the range of the function f, so that the composite function is defined. Number one, and then the function f should be is complex differentiable at a, and the function g is complex differentiable at f of a. Then the composite function is complex differentiable at a and the derivative of the composite function g composed with f prime a equal to g prime of f of a times f prime of a. That is a chain rule. Alright. So now we state the important chain rule. Let f from omega 1 to c, g from omega to c be given functions such that the range of the function f is contained in the domain of the function g, so that the composite function is well defined. Assume f is complex differentiable at a from coming from omega 1 and g is complex differentiable at the point f of a coming from omega 2. Then the composite function GOF from omega 1 to c is complex differentiable at a, and the derivative of g composed with f prime of a is given to be g prime of f of a into f prime of a. This is the complete theorem. Okay, just writing this part is not enough. When you ask somebody to state the chain rule, it is not just enough to write this, you have to write the whole thing. The composite function should be defined, the individual pieces should be differentiable at a and f of a respectively. Then the first part of the theorem says that the composite function is differentiable. Now that it is differentiable, it makes sense to ask what is the derivative, and that is the final statement. GOF prime of a is g prime of f of a into f prime of a. The proof of the chain rule is non-trivial. The proof of the chain rule is quite non-trivial, but the proof is that you give for the real variables case goes over into the complex variables case. There is no difference as far as the proof is concerned, but the proof is non-trivial both in the real variable case as well as in the complex variable case. What is the proof in the real variable case? Do you recall? Do you recall proving it anytime seriously? In many calculus texts, you will see delta y by delta x is delta y by delta u into delta u by delta x. Let delta x go to 0, dy by dx equal to dy by du into du by dx. This argument is very formal and quite imprecise. It is okay as a first attempt perhaps. You may probably have this as a sort of a first attempt at trying to prove the chain rule, but then you have to be careful. Reason why, there are two things you have to ask yourself. Why is it that the delta u goes to 0 as delta x goes to 0? That is because u is differentiable as a function of x, and so differentiability implies continuity. That is the reason that as delta x goes to 0, delta u also goes to 0. There is a second and serious difficulty here, that even in the elementary calculus courses, the x is the independent variable and u is a dependent variable, and delta x is an increment in the independent variable. So, delta x is not 0 when you write delta y by delta x, but then u is a dependent variable, you have no control over delta u. Moment delta x is given to you, the delta u will you have no control over delta u. Delta u may be 0 even though delta x is not 0. So, you cannot write delta y by delta x equal to delta y by delta u into delta u by delta x. So, you may give a formal argument, this formal argument can be given in a calculus course, but it has to be pointed out to the students that this is not a rigorous proof. This is a very imprecise formal argument which is far from a correct proof, and this has to be tightened up considerably. And why is this delta y by delta x business not a very not very precise? That also you should point out to your students. You should understand why that argument is imprecise and why, where is the difficulty. Okay. So, we will not prove this here. You can look at Courant, you can look at Courant John or whatever. Next, let us come to the very important topic, Cauchy-Riemann equations. This is really the sort of a subtopic, if you will, Cauchy-Riemann equations. Now, suppose you have a function f defined on omega, which is complex differentiable on omega. In fact, it is enough that it is complex differentiable at a point A in omega, because whatever we are going to be doing, we are going to be concentrating at a given point A. But anyway, I am not going to state the theorem in utmost generality. Now, f takes its values in C, correct? So, it will have a real part and f will have a imaginary part. The real part is u and the imaginary part is v, correct? And f is a function of a complex variable. The complex variable has a x plus has a real part x and an imaginary part y. So, this u will depend upon x and y and the v will also depend upon x and y. So, u is a function of two variables and v is a function of two variables. And you can think of omega as a subset of R2, because the complex number, remember, can be viewed as an ordered pair. Now, so this function f has been assumed to be complex differentiable. Then it turns out that this u and the v must satisfy a system of partial differential equations, a coupled system of PDEs, del u by del x equal to del v by del y, del u by del y equal to minus del v by del x. This coupled system of PDEs is called the Cauchy-Riemann equations, pair of Cauchy-Riemann equations. So, for example, suppose I take a function f as f of x plus iy equal to x squared plus y squared. Take the function f of x plus iy equal to x squared plus y squared. Prima facie, it is a very nice function, it is a polynomial in x and y. So, what is the u? U is x squared plus y squared, v is 0. What is del u by del x? 2x. Is it equal to del v by del y? No. Yeah. What about del u by del y? 2y. Is it equal to del v by del x? No. The only place where the Cauchy-Riemann equation is satisfied is the origin. At no other place is it does it hold. So, an innocent thing like f of x plus iy equal to x squared plus y squared is not complex differentiable, correct. So, complex differentiable functions are rather special They are very distinguished objects. The real and imaginary part, it is not just enough that the real and imaginary parts should be nice. The real part can be a polynomial and the imaginary part can also be a polynomial, and still when you put them together and make it a u plus iv, it will not be complex differentiable in general unless the Cauchy-Riemann equations are satisfied. So, the Cauchy-Riemann equations put in a very stringent condition on u plus iv to be complex differentiable. So, the requirement that a function u plus iv be complex differentiable is a very stringent requirement. It is a stringent requirement because the pair u and v have to satisfy a pair of partial differential equations. Right? Can't just be, you can't just take a nice u and a nice v, put them together and get some nice function and expect it to be complex differentiable. No, it will not be complex differentiable unless it satisfies the Cauchy-Riemann equations. Is this clear? Let us look at the proof of this. Let us derive the system of partial differential equations. Idea is very simple. What is the hypothesis? Hypothesis is that the function should be complex differentiable. What is the meaning of complex differentiability? The meaning of complex differentiability is that f of a plus h minus f of a upon h limit as h tends to 0 must exist. That is all that you have at your disposal. And from this bare minimum, you have to derive two partial differential equations. And there is one and only one way of getting it. Observe that the h tends to 0 through complex directions, correct? H is a complex variable now. H is a point in the complex plane and this h is going to 0. So, h as a point in the complex plane is going to 0. It can go to 0 in several different directions. In particular, it can go to 0 in the along the real direction. It can go to 0 in the imaginary direction. No matter how it goes to 0, you should get the same value. So, I will allow the h to go to 0 through real values and see what happens. I will allow the h to go to 0 through purely imaginary values, see what happens. I will compare the results and equate the real parts and equate the imaginary parts. A pair of equations will fall out and they will be the Cauchy-Riemann equations, correct? That is the argument, plain and simple. It is very straightforward derivation and we just let us carry it out. Okay, so let us fix a point x naught y naught and call it z naught, right? Since f prime z naught exists, limit as h tends to 0, f of z naught plus h minus f of z naught upon h exists. We take h to be real and then along the real axis h goes to 0, and let us write this condition down. F of z naught plus h minus f of z naught upon h is what? It is limit as h tends to 0 1 over h. F is what? U plus iv. Z naught is what? X naught plus iy naught or x naught comma y naught. But what is h? Mind you, h is real. So, when I say z naught plus h, it will be x naught plus h comma y naught. All right. Likewise, here v of x naught plus h comma y naught, right? U plus iv minus f of z naught, u of x naught y naught minus iv of x naught y naught, correct? Now, separate the real and imaginary parts. It is what? U of x naught plus h comma y naught minus u of x naught comma y naught divided by h. What is that? Del u by del x at x naught comma y naught plus I times you have v of x naught plus h y naught minus v of x naught comma y naught divided by h, that is del v by del x at x naught y naught. right, that is star. Now we let h go to 0 through imaginary values, purely imaginary values. Okay. So let h go to 0 through purely imaginary values. Instead of h, I am going to take I t, where t goes to 0 and t real. Right. So again 1 over I is minus I, 1 over I is minus I. So minus I by t, f of z naught plus I t. It will be u of x naught comma y naught plus t plus I times v of x naught comma y naught plus t minus u of x naught y naught minus I v of x naught y naught. These two things, u of x naught comma y naught plus t minus u of x naught comma y naught will divided by t, and t is going to 0. What are you going to get? Del u by del y plus I times del v by del y, and there is a minus I outside. So what is it? Minus I into plus I is 1. So del v by del y minus I times del u by del y, correct? This is a double star, and so now we will put the star and the double star together. This number should be equal to this number, correct? And so you have to equate the real parts and you have to equate the imaginary parts. When you equate the real parts, what do you get? Del u by del x equal to del v by del y, del u by del y equal to minus del v by del x. What is it? It is precisely the pair of Cauchy-Riemann equations. Clear how the Cauchy-Riemann equations come in? Right? Comparing star and double star, you get the Cauchy-Riemann equations. The theorem, in the theorem I said that f is complex differentiable throughout omega. That is not really required. We are just focused our attention at the point z naught, and we obtained the Cauchy-Riemann equations at the point x naught comma y naught, correct? It is a pointwise result, alright. That is what the remark says. The remark says that it is a pointwise result. Although the theorem was stated for simplicity, and I put too many hypotheses in the theorem, it is difficult for you to take it. So I stated the theorem in much more with more hypotheses, but that is not required. Right? So this is the thing. Right? So now from complex differentiability, we have a pair of partial differential equations, the Cauchy-Riemann equations. So complex differentiability implies that the real and imaginary parts u and v satisfies a pair of coupled PDEs, the Cauchy-Riemann equations. Now you want to understand whether the converse is true. Suppose you have u and v given to you, and they satisfy the pair of Cauchy-Riemann equations. Will the function f equal to u plus iv be complex differentiable? Well, we are going to answer as no in general, but we are going to prove the theorem with slightly more hypothesis. In fact, under very broad conditions it is true. It is true under very general conditions, that if the Cauchy-Riemann equations are satisfied, then the function f equal to u plus iv is complex differentiable, but to prove the theorem in generality is quite difficult. The theorem in a very general context is called the Luhmann-Menshoff theorem. It is a very difficult theorem to prove, and we do not need all this generality. All that we really need is summarized in the following theorem. Suppose you have a function f from omega to c with f equal, with the real part of f is u and imaginary part of f is v, that is f is u plus iv. You assume that del u by del x, del u by del y, del v by del x and del v by del y exist throughout omega, they satisfy the Cauchy-Riemann equations and they are continuous. You assume that the 4 partial derivatives del u by del x, del u by del y, del v by del x, del v by del y are continuous. Then we are able to prove without much difficulty that the function u plus iv is complex differentiable. That is not difficult, but the proof I will not present here, because in a 10-day workshop I can't be proving each and everything. You could look up Kreyszig's book, or you could look up Courant and Fritz John's book, or you could look up Churchill's book, any of the several standard books on complex analysis. Once again I emphasize the continuity of the partial derivatives can be relaxed, can be dropped, and it can be replaced by much weaker conditions. And this theorem in this great generality is called the Luhmann-Menshoff theorem. We do not need the Luhmann-Menshoff theorem for our work. This theorem that I have stated here is much easier to prove, far more easier to prove than the Luhmann-Menshoff theorem, and this version is more than adequate for our purpose. Okay. We do not need the theorem in great generality. So all that we really need is described here. Alright. Proof we will not do. Proof is simple. What you have to do is you write f of x, you write f of z naught plus h minus f of z naught. You have to break it up into the real and imaginary part, and as usual you have to add and subtract terms. Remember the trick, when you prove the product rule, etc., you add and subtract term. To add and subtract terms, and you have to use the mean value theorem. You have to use the mean value theorem, Lagrange's mean value theorem. That is a crucial thing. That is a crucial ingredient in the proof. And then you have to subtract the ux plus ivx, and then you have to estimate. It is not difficult at all, but it is a little lengthy. It will take a little more time than the previous one. The necessary condition was easy. Sufficient condition will take longer, perhaps 3 or 4 slides, but I really do not have time to prove everything over here, but we will assume this, and you can read the proof yourself, and I am telling you exactly what is involved in the proof. You have to simply write down f of x, z naught plus h minus f of z naught, write the real and imaginary parts, add and subtract terms, because you see the h is complex. F of z naught plus h minus f of z, the h is complex, it will be h1 plus ih2. So it will be u of x naught plus h1 comma y naught plus h2 minus u of x naught y naught. So you know exactly what the terms you have to add and subtract, and then you have to apply the mean value theorem. Carry it out, I mean read the proof from Courant John, and can. Alright. So now let us take up a few examples. One verifies using the definition, that is directly from first principles if you like, that fz equal to z is complex differentiable. Limit exists, f of z naught plus h minus f of z naught upon h. Limit exists and the limit is 1. So this function f of z equal to z is complex differentiable. Constant function, is it complex differentiable? Does the limit exist from first principles? Yes, and the answer is 0. So so the constant function is complex differentiable. F of z equal to z is complex differentiable. So now you can apply the rules of calculus, sum, products, quotients. So from 1 and z, or from constant and functions and z, what can you construct? All the polynomials. So polynomials are complex differentiable, correct? Rational functions, ratios of two polynomials, pz upon qz, they are complex differentiable, correct? Rational functions are complex differentiable except at points where the denominator is 0, correct? So rational functions are complex differentiable. That is all that we can get from elementary considerations. To get anything more, you need to do a little more work. And here is where the Cauchy-Riemann equations come in. Now, because of the two theorems that we have proved, I could take a pair of functions u and v such that del u by del x equal to del v by del y, del u by del y equal to minus del v by del x, Cauchy-Riemann equations are satisfied, and the 4 partial derivatives are all continuous, then u plus iv will be complex differentiable. So, now I have to produce pairs u and v with this property, correct, to generate anything other than rational functions. I can easily produce a rational function just by the definition and the rules of calculus, but to get anything more I need to do some work. Alright. So, let us look at this particular function e to the power x cos y plus I e to the power x sin y. What is your u? Your u is e to the power x cos y and your v is e to the power x sin y. What is del u by del x? E to the power x cos y is the same as del v by del y. Del u by del y is minus e to the power x sin y is the same as del v minus del v by del x. So, this pair of functions e to the power x cos y and e to the power x sin y satisfies the Cauchy-Riemann equations, and the 4 partial derivatives, are they continuous? Yes, they are continuous. And so, e to the power x cos y plus I e to the power x sin y is a complex differentiable function, correct. So, is this a rational function? This is not a rational function. This is not the ratio of 2 polynomials. How do you know it is not a rational function? It is, I mean, I have given you an example, but up until before this, what was our stock of complex differentiable functions? Set of all rational functions. Now I am claiming that using the Cauchy-Riemann equations, I have produced something which is outside the realm of rational functions. How do I know that this is not a rational function? Right? This is an important question, right? Suppose a student asks you this, how do I know? You claim that using the definition and the rules of calculus, I have that f of z equal to z is complex differentiable, constants are complex differentiable, polynomials are complex differentiable, rational functions are complex differentiable. We are very happy. We have a nice, rich class of complex differentiable functions, but this is not rich enough, right? I want something which is not a rational function, which is also complex differentiable. Okay, the Cauchy-Riemann equations have given us a new example, e to the power x cos y plus I e to the power x sin y. That is complex differentiable because it satisfies the Cauchy-Riemann equation. Now the question is, why is this not a rational function? If it is a rational function, not a rational number, then e to the power x cos y plus I e to the power x sin y is pz upon qz, alright, yeah, sorry, polynomial over the complex numbers, correct.
And when polynomial, then under the theorem of algebra says that q of z has a root in C.
Q of z has a root in C, but then but then if it is a non-constant polynomial, but qz could be a constant polynomial. You are right, you are very close, I mean you are on the right track.